Hello students, welcome to EPG Pathshala. I am Dr. Manjula Sharma from University of Delhi. Today we are going to discuss about the module circuit components, which includes resistors, inductors and capacitors. From the paper Measurement and Instrumentation. From this module, students may get to know about the following topics. First, the resistors, and we will discuss about the materials suitable for use as resistors. Second, the inductors. We will study the standards of inductance, the formers of the inductance coils, and the coils used for the inductance coils. Thirdly, the capacitors, where we will study the capacitance standards. So students, we know that it is almost impossible to manufacture a component so that it has only one property. For example, a resistor has an associated inductance and capacitance. A capacitor has a leakage resistance and an inductor has resistance and interturn capacitance. The impurities present in a component produce unwanted quantities which are called residues. However, a particular quantity like resistance in a resistor, capacitance in a capacitor, inductance in an inductor may be made to dominate, and so the effect of residues is very small, and it is possible to design pure components for specified limits of accuracy. Now students, let us see the resistors. Resistive networks and resistors are extensively used in instrumentation systems and for measurement work. Resistors must satisfy some extremely important properties for precision measurement work, such as they must be stable or show permanence with time, as it is required to avoid the change in value of resistance with time. They must have robust construction and small temperature coefficient. It is required in order that the variation in resistance values owing to change in temperature is small. They should have low thermoelectric EMF with copper. The thermoelectric EMF with copper is particularly important in bridge networks and potentiometers, as large measuring errors may occur even if the thermoelectric EMF is a few electron volts. They should have high resistivity. It is required in order that the size of the resistors is small. The resistor material should show resistance to oxidation, corrosion, and moisture. Also, they should have ease in manufacture and should be cheap. Now let us see what are the materials which can be suitable for use as resistors. A single material cannot possess all the above mentioned properties, and hence only that material is selected which is best suited for the particular case. The most widely used materials for precision resistors are: first, manganese. It is an alloy of copper, manganese and nickel and is universally used as resistance material for precision resistors and for resistance measuring apparatus. It has a nominal composition of 84% copper, 12% manganese and 4% nickel. Manganese has a resistivity of 0.45 to 0.50 multiplied by 10 raised to minus 6 ohm meter, which is nearly 25 times that of copper. It also develops a thermoelectric force against copper of 2 to 3 microvolt per degree Celsius. With proper heat treatment, it gives a suitable resistance value with time. The foremost property of manganese is that It has almost a zero temperature coefficient of resistance, near about room temperatures. Manganese is used for resistances of very high accuracy when the temperature rise is not expected to rise above 15 to 20 degrees Celsius. The second material used for resistors is constantan. These are basically a series of alloys of nickel and copper containing 40 to 60% nickel with a small amount of manganese in order to improve their mechanical properties. All these alloys exhibit similar electrical properties. They are sold as constantan or under various trade names for use as thermocouple materials. They have thermoelectric powers against copper of about 40 microvolt per degree Celsius. However, except for their large thermoelectric powers, the electrical properties of these alloys are remarkably similar to those of manganese. Constantan has a resistivity at ordinary temperatures of about 25 times that of copper, which is about same as manganese. It is corrosion resistant, inexpensive, and easy to work with. This can be easily soft soldered to copper. Constantan finds extensive use in cases where its high thermoelectric power against copper is not a disadvantage. For example, it is frequently used in resistors designed for AC operation. It also finds application in resistors of 1000 ohm and above, as in voltmeter multipliers, where the thermal EMF generated at copper constantan junction is negligibly small as compared to the EMF being measured. Nickel chromium alloys. These alloys have a somewhat higher temperature coefficient of resistance than that of manganese and constantan. Nichrome is an example of this class of alloys. These alloys cannot be used in precision resistances. Nichrome has a very high resistivity, which is about 50 times that of copper, and it resists corrosion even at very high temperatures. Nichrome is often used in rougher class of resistors, where small size is all important or where the operating temperatures are high. However, these alloys are difficult to solder. Alloy appears to be very promising for some applications. It is made with slightly over 2% of chromium. This alloy has a resistivity at room temperature of about 20 times that of copper. Its temperature coefficient can be made extremely small by making it at fairly low temperatures. It has a thermoelectric power of 7 or 8 microvolt per degree Celsius with copper. For many applications, the extremely small temperature coefficient of gold chromium alloys make their use desirable. They are used for making heat-resistant standard resistors. Although its resistance temperature coefficient is small near room temperature, the range over which the coefficient is small is 20 to 30 degrees Celsius. Students, now let us start with the inductors. First, the standards of inductance. Both the self and mutual inductances depend upon their physical dimensions together with the number of turns in the coil. For the designing and construction of inductance standards, few considerations must be taken care of. such as the design and construction should be such that a rigidly standard accurate formula exists relating the value of inductance with the physical dimensions. The design should be such that accurate measurement of physical dimensions is possible. The materials used should be such that the value of inductance remains constant irrespective of the environmental and circuit conditions. This requires that the materials used should be such that their dimensions do not change with time, temperature, and humidity. The inductance should be independent of the value of the passing current. This requires that no ferromagnetic materials should be used. When we use ferromagnetic materials, the value of permeability and hence inductance is dependent upon flux density, which in turn depends upon the current flowing in the coil. Hence, the inductance of an inductor constructed with ferromagnetic cores depends upon the value of the current passing. In order for inductance to be independent of the current passing, air-cooled coils should be used for standards of inductance. The resistance of the windings should be very low as compared with their inductance, or the inductor should have a high L by R ratio. The ratio of inductive reactance to resistance of a coil is known as its storage factor or Q factor. The Q factor is defined as Q is equal to omega L by R. The effective inductance and resistance should be least affected by frequency. This requires that there should be minimal losses. Ferromagnetic materials should never be used as eddy current losses in them are appreciable. The use of inductors having ferromagnetic cores is completely ruled out for high frequency application. The coils should use stranded wires, as otherwise the eddy current losses in conductors become large, especially at higher frequencies. The use of metallic parts should be avoided as the eddy currents induced in them affect the value of inductance. The inductor should be so designed that capacitive effects are negligible. This is particularly important for inductors working at higher frequencies, where the interturned capacitance may drastically change the effective value of inductance. The inductor should be desirably unaffected by external magnetic fields and should produce a minimum interfering field of its own. Formers of inductance coils. Marble is used for making formers or bobbins for the coils. The reason for selecting marble are that it does not warp and is unaffected by atmospheric conditions. It has a high electrical resistance and hence acts like a perfect insulator. It is a non-magnetic material and can be easily machined. It is pretty cheap and easy to work with, or by using an iron core. Students, now let us see the capacitors. Due to several factors, capacitors do not show perfect and constant capacitance at all frequencies. There are ohmic losses in the plates and connecting wires, interfacial polarization, and power loss in dielectric, etc. Therefore, a capacitor can be represented by an equivalent circuit as shown in figure 1a. Here, the resistance represents the losses. In the case of air and most other cases, the losses in the dielectric are very small, and hence capacitors using these dielectrics may be regarded as perfect. Figure 1b represents the phasor diagram of a dielectric when a potential difference is applied across it. The various terms so used are defined as follows. V represents the applied voltage in volts. IC is the capacitive current in amperes. IR represents the active component of current, which is again in amperes. C represents the capacitance in farads. R represents the resistance in ohms. Omega represents the 2 pi f, the frequency in radian per second. F represents the frequency of supply in hertz. Power factor of a dielectric is the cosine of the angle between phasors representing the voltage across the dielectric and the total current through it when a sinusoidal AC voltage is applied across it. So, the power factor cos phi is equal to cos of 90 minus delta, which is equal to sine delta, where delta is called the loss angle of the capacitor. The value of delta is very small. Therefore, sine delta is equivalent to tan delta is in turn equivalent to delta. The dielectric loss is given by V multiplied by I multiplied by cos of 90 minus delta, which is equal to Vi sine delta, which is again equivalent to V into sine delta multiplied by I naught divided by cos delta, which gives V I naught tan delta. Thus, the final term for the dielectric loss is given by omega multiplied by C multiplied by V square multiplied by tan delta, where I naught is equal to omega C V. Also, tan delta is equal to IR by I naught, which in turn is equal to 1 by omega CR. Figure 2a shows the capacitor and figure 2b the phasor diagram of this arrangement of capacitor, where C is equal to equivalent series capacitance in farad, R is the equivalent series resistance in ohms. Here the power loss is given by Vi cos phi is equal to Vi sin delta. Thus, the final term for power loss is given by I square tan delta divided by omega c, where tan delta is equal to IR divided by 1 by omega c. Thus, tan delta is given by omega CR. The power factor of a capacitor is very good test of its quality. Factor of capacitor. Dissipation factor D is given by omega CR, which is equal to 1 by omega C capital R. So students, now let us see the capacitance standards, primary standards. The dimensions of capacitance are those of length if the permittivity epsilon is taken as dimensionless. Therefore, values of primary standards of capacitance can be known by measuring lengths. The dimensions of such capacitors should be very accurately known in order that a primary standard is constructed. Air is usually used as the dielectric, as it is the only dielectric whose permittivity is definitely known and which is free from absorption and dielectric loss. Three types of constructions have been used for primary standards. First, two concentric spheres. Second, two concentric cylinders. Third, two parallel plates with guard rings. Parallel plate construction is normally not used. The concentric cylinder construction is shown in figure 3. Air capacitors have extremely low losses, usually assumed to be zero. If the dielectric which supports the insulated electrodes is good insulating material and is placed in a region of low field strength. Therefore, air capacitors seem at first consideration to be well suited as primary electrical standards. It has been found difficult, however, to secure the extremely high stability needed for this purpose. Even carefully treated metal parts warp somewhat with time, and so permanency is not that much as is desired in primary standards. So students, let us summarize what we learned in this module. In this module, we studied the various circuit components such as resistors, inductors, and capacitors. We discussed that the resistors are extensively used in instrumentation systems and for measurement work. Resistors must satisfy some extremely important properties for precision measurement work, such as they must be stable or show permanence with time, as it is required to avoid the change in value of resistance with time. We also discussed the various materials suitable for use as resistors, such as manganese, constantan, nickel chromium alloys, and gold chromium alloys. Secondly, we studied the inductors. We saw that for the designing and construction of inductance standards, a few considerations must be taken care of, such as the design and construction should be such that a rigidly standard accurate formula exists relating the value of inductance with the physical dimensions. We discussed the formers of inductance coils, which are made of marble. Third main component discussed in this module is capacitors. Due to several factors, capacitors do not show perfect and constant capacitance at all frequencies. There are ohmic losses in the plates and connecting wires, interfacial polarization and power loss in dielectric, and several other factors. We studied that the dimensions of capacitance are those of length if the permittivity epsilon is taken as dimensionless. Therefore, values of primary standards of capacitance can be known by measuring lengths. We saw that three types of constructions have been used for primary standards of capacitors. First, two concentric spheres. Second, two concentric cylinders. Third, two parallel plates with guard rings. Out of these, parallel plate construction is normally not used, and the concentric cylinder construction has been discussed in the module. Thank you.